Good morning and welcome to Advanced Electrical Networks. This is lecture 13. A quick recap of what we were doing in the last class. We basically were wondering what would happen to the transfer function of a biquad if the op-amp was not ideal, and the model we assumed for the op-amp is basically we assume that the gain of the op-amp is of the form omega u by s, and we now know why that model comes about, where you assume that the op-amp is typically realized using Miller compensation, and therefore you have a dominant pole and a large DC gain. The DC gain, of course, for all practical purposes can be neglected since it's so high. So all that remains is that the op-amp, instead of having an infinite bandwidth, you can think of it as having a transfer function over the useful frequency range of omega u by s. Omega u is the gain bandwidth product of the op-amp in radians per second, and when we analyze this integrator with the gain of the op-amp being omega u over s rather than just simply infinity, the integrator transfer function we got was minus 1 over SCR times, or this is approximately minus 1 over SCR times 1 over 1 plus S over omega u, right. So, intuitively what this equation is telling us is that, well, this is recall that this is the ideal transfer function that you would get if omega u tends to infinity, right. Now, what this is telling you is that you have this within quotes practical integrator where you have a real op-amp but not an ideal one, and the output is of course an integrated version of the input, except that there is a delay in the output, and that delay to first order is simply a time delay of minus 1 over delay is basically 1 over omega u seconds, and that's as far as the integrator is concerned. And remember that the biquad is basically consists of integrate, invert, integrate, this is a damping resistor, okay, and for simplicity we simply use the same valued resistors everywhere, and this is has an omega naught which is 1 over RC, and so this becomes minus omega naught over S times 1 over 1 plus S by omega u, and the quality factor is Q. The transfer function that the low pass transfer function that we get is VLP of S by VI of S, as we discussed, is minus 1 over S square by omega naught square plus S over omega naught Q plus 1, provided what? If the op-amps are ideal. The question now is, oops, our op-amps are not ideal, therefore our integrators are not ideal, okay, and then what will this do to our biquadratic transfer function? As we were discussing yesterday, this is truly now a fifth order transfer function, right. Our only hope is that omega u is so high that in the frequency region of interest it still can be approximated by a second order transfer. And we also saw yesterday that if you are interested in the magnitude response, the magnitude response is simply, or the frequency response for that matter, is simply you travel along the j omega axis in the S plane, right, and what do? If the transfer function can be represented as S minus P1 into S minus P1 star, right, there are two poles and the DC gain is 1. So, this must be P1 star, correct. So, why do we do this? Well, this gives us a nice way to interpret h of j omega. So, let us say this is P1 star is somewhere here, and this is j omega, all right, and to find h of to find the complex number h of j omega, well, you draw the vector j omega minus P1, which basically is this guy here, and j omega minus P1 star, which is that guy there, okay. And so, if you call this vector R1 and then if you call this vector R2, then mod h of j omega is simply P1 star by R1 R2, right. We have seen this, you have seen this in your earlier classes multiple times. So, in effect, when we are when we are plotting h of j omega, what we are actually doing is starting at the origin and keep going along the j omega axis. At each point on the j omega axis, you basically draw these arrows R1 and R2 and compute this. Is this clear? Right. So, now for the time being, just assume that this op-amp is ideal, so that the inversion is obtained for free, right, without any bandwidth limitation. It turns out that and those of you who have taken analog IC design would know this already. It turns out that most ICs today, the signal path is always realized in what is called fully differential fashion, right. How many of you are familiar with what fully differential means? How many of you have taken analog IC design? Okay, and the others are taking it, so you will find out. So, whenever you realize circuits in fully differential fashion, one of the advantages of doing that is that apart from the fact that it is immune to common mode disturbances and a whole lot of nice stuff like that, another aspect is that inversion is obtained for free, right. It is simply obtained by interchanging the wires, right. So, this our assumption that this inverting amplifier, basically let us assume, at least for the time being, that it is ideal, is not a bad one. So, if that is the case, then the only difference between the ideal one and the actual one is, remember, the ideal integrator is minus omega naught by S, the actual one is minus omega naught over S times 1 plus S over omega u. So, if you stare at these two expressions, what do you think you see? In other words, how will you express the non-ideal transfer function in terms of the ideal one? Stare at these two. All that we have done is replace the ideal integrator with a non-ideal one. So, the question is, is there a simple way of figuring out what the non-ideal transfer function will be in terms of the ideal? Well, all that we are doing, if you stare at it carefully, is replace omega naught by s with omega naught by s times 1 plus s by omega u, which is equivalent to saying, in fact, there is a simpler way of thinking about it. It is simply replacing s with s plus 1 s times 1 plus s over omega u. Correct? And therefore, H non-ideal of S is simply equals simply, yes. So, now how do you express the non-ideal transfer function in terms of the ideal one? H ideal of S times 1 plus S over omega. Correct? Does it make sense? And while this we are talking about a biquad, this also applies to any high order filter, because if every integrator is modified according to this relationship, then it is simply replacing whatever transfer function you have. If the integrators are messed up according to this, then it is simply a matter of replacing S with the new transfer function, or the non-ideal transfer function is simply the ideal transfer function with S replaced by S times 1 plus S over omega u, right. And what are we interested in? We are interested in finding H non-ideal of j omega, right. Okay. And how is that related to H ideal of j omega? Therefore, we know how H non-ideal of S is related to H ideal of S. How do you relate H non-ideal of j omega to H ideal of j omega? Yes? Very good. It is basically simply replace S with j omega, and therefore H ideal of j omega minus omega square over omega. Correct? So, how do we interpret this equation? Remember, if we had the original transfer function, right, this is P1 and this is P1 star. To find H ideal of S, H ideal of j omega, we would go along the j omega axis along this path as shown there. Correct? Now, the non-ideal magnitude response or frequency response, what is this equation telling us? We now, instead of traveling along the j omega axis, you go along a path which is j omega minus omega square by omega u, right. And how does that path look like? Okay, well, and remember that omega u, and let me also kind of draw your attention to the fact that this is approximately omega naught, okay, all right. And how does this path j omega minus omega square by omega u look like? And omega u, remember, is much greater than omega naught. So, how does this path look like? At DC, it will be 0, right. As you keep increasing omega, what happens? It deviates from the j omega axis. Does it go into the left half S plane or the right half S plane? Left half S plane. And the trajectory you are taking, I am grossly exaggerating here so that you can see it, but it takes some trajectory like that. All right. Okay. And let me also draw your attention to another fact. What comment can we make about that part, the x coordinate of P1? What is that distance? Omega naught by 2q. And what is the definition of q? It is omega naught, which is the radius corresponding to P1, divided by the distance to the j omega, I mean how close it is to the region of stability, to the edge of stability, and that is omega naught by 2q. So, the ratio of the two is just times 1/2, which is q. That is the definition of q, right. Now, what has happened now? As you keep going along the red path as shown here, what comment can you make? At what point is the gain the highest? At what point on that red path would the magnitude response peak or become very, very large? Technically it is perpendicular, but this thing is going so what do you call the slow, I mean because omega u is much greater than omega naught, right. It is technically a parabola, but for all practical purposes that it is almost parallel to the x axis, to the y axis, right. So, to first order therefore, the peak in the transfer function, right, or the distance to the edge of the region of instability is now, is it smaller or larger? It is smaller, right. So, therefore, do you think the filter is within quotes more stable or less stable now? Less stable, and intuitively that makes sense, right. We have a negative feedback loop. In that loop now there is extra delay because of finite bandwidth of the op amps, and as a result the feedback loop becomes is tending to instability. So, what is the distance now? What just look at it and tell me, give me a simple, just use geometry and tell me what this distance is now. It is simply omega naught by 2q minus that much, right. And so, what is that? It is omega naught by 2q minus omega naught square by omega u, correct. Now, if you had a fictitious biquad with ideal op amps, what q would it have if the distance to the j omega axis was the same? Do you understand the question? Suppose we had a second order biquad with ideal op amps, right, okay. What q would it have if its distance to the j omega axis was the same, which is namely omega naught by 2q minus omega naught square by omega u? How would we find that out? So, basically we have a fictitious biquad, we do not know its quality factor, but we know that the distance, if you denote the quality factor by q hat, then the distance from that P1 of that biquad to the j omega axis would basically be omega naught by 2q hat, all right. So, what is, how is, how is q hat related to q? So, which basically means 1 over q hat equals 1 over q minus 2 omega naught square over 2 omega over omega. Okay, what is the sanity check? Does this pass sanity check? As omega u tends to infinity, we expect that q hat basically tends to q. So, what is q hat? What is q hat in terms of q? Can you express that as q times something, so that when that something, when omega u tends to infinity, that something tends to 1. Very good, very good. Q divided by, very good. All right. Okay. So, q hat, I mean, so is q hat higher than q or smaller than q? That again makes sense, right? Because so in other words, the moment the op amp has got a finite gain bandwidth product, because of the excess delay added by the op amps, right, the quality factor appears to have been enhanced, right, indicating in English that the poles are moving closer to the j omega axis, right, pushing the filter transfer function closer to instability, right, and the Q hat, I mean the Q is enhanced according to this relationship, right. So, if you want a quality factor which is close to what you intended, right, what comment can you make about the gain bandwidth product of the op amp? I mean, of course, large is of course the first order zeroth order statement we can make, right. Can we what is the meaning of large now? No, think carefully. What must be much smaller than 1? What is the meaning of large omega u? So, this factor must be much smaller than 1. So, the notion of what a large, the gain bandwidth product of the op amp must be large enough. What that large enough means is that omega u must be much greater than 2 omega naught, right. We might have simple mindedly assumed that omega u being much greater than omega naught is probably all that it takes. You can see that the constraint is much more is much tighter, right. So, basically we expect to see omega u to be much greater than 2 omega naught. Does it make sense, people?